Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video introduces the uniform probability distribution and shows how to calculate probabilities with it using an old school approach. Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video introduces the uniform probability distribution and shows how to use it to calculate probabilities using the old school approach. Let's get started. Okay, uniform distribution is the first continuous probability distribution that we're going to examine. And we do this because it's really probably the most simple example of a continuous probability distribution. So you can see the shape that the uniform distribution makes. It's rectangular in form. And so we go along here along the axis, and there's a point at which it comes up. And then it stays uniform. So it stays at the same value until it's brought down again and then continues back along the x-axis. This is a uniform probability distribution. We can use the area underneath the density curve to find a probability. Just as we said in the last mini lecture, because the area underneath the density curve is equal to 1, we can correspond the area that's we're looking for underneath the curve with a certain probability. So to demonstrate that, let's actually look at an example problem where we have a simple DC circuit. DC means direct current. So this is the kind of electric current that you're going to get out of, say, an alkaline battery. And we're connecting it to a 0.5 volt power supply. So we have the circuit connected, and then we start the clock. The clock's ticking. So here we've got time here on our x-axis. And once we start the clock, it starts to tick. And then 1 second in to our time, we actually turn the circuit on. So we connect it up, close the circuit, and the voltage jumps up to 0.5 volt. This is the voltage being supplied by our power supply. We then leave it on for 2 seconds. So that brings us over here to 3 seconds. And then we turn it off. So then the voltage comes back down and then continues here along the x-axis. So here we have an example of a uniform distribution. Now, what is the probability that a randomly selected time will be greater than 2.5 seconds? Okay, this is really simple once you know what you're doing. So first, we're going to shade the area that's greater than 2.5 seconds underneath the density curve. So we start here at x equals 2.5, and we're going to shade everything to the right because this is the area that's greater than 2.5 seconds. Notice that the shaded curve, because it's a uniform distribution, is a rectangle. So to find the area underneath the curve for the portion that's shaded, all we simply need to do is find the area for that rectangle. The area for a rectangle is simply the length of the rectangle times its width. And we can get those values by looking at our graph. So the height of the rectangle, or the length if you will, is going to be 1/2. Because we have a 1/2 volt power supply. So the voltage here on our y-axis, that's the height of the rectangle. And then the width of the rectangle is going to be the difference between the 3 here on this edge and the 2.5 here on this edge. So this is really 1/2. That's the width there of your rectangle. So if I just multiply that out, length times width, I get 0.25 or 1/4. And that is the probability that a randomly selected time will be greater than 2.5 seconds. Let's look at some key things to look at when solving uniform distribution problems. So usually when you get a problem involving a uniform distribution, you're going to be asked to find a probability. And it's going to be expected that you're going to find that probability by calculating the area under the curve. Oftentimes, the height of a uniform distribution is given when describing the distribution, but sometimes it isn't. And so in order to get that value for the rectangle that you're going to shade underneath your density curve, you're going to need both dimensions. And it's going to be easy to get the dimension along the x-axis, but the dimension along the y-axis, if it's not given to you in the problem, then you're not going to know it. And in that case, you have to assume the height is a function of the range of the distribution using this little formula right here. So you simply take the max value, the min value, subtract the 2 out, and then take the reciprocal of that. So 1 over that difference, that gives you the height of the rectangle in your uniform distribution. Now, an easy way to solve these problems old school style is simply to draw a picture. I'm really visual when I learn, so I like drawing stuff because it helps me to see more what's going on. So don't be afraid to just start out by drawing a rectangle. Draw the rectangle that you need. Okay, this is going to be the shape that you're going to find underneath the curve for all uniform distribution problems. So start out by drawing a rectangle. Then you want to label the range of your distribution. Find your max and min values. It's uniformly distributed between two values. Those are your max and min values. Next, you're going to calculate the height. If it's not given to you in the problem, then of course you're going to use that little formula there to find it. And then you're going to identify the area underneath the rectangle that's shaded that corresponds with your probability. So in this instance here, we're showing that we're looking for the probability that's half the range. So that's greater than halfway between the min and the max. This is just to show you for an example, but you're going to have to adjust this for whatever your problem actually tells you to look for. Then once you get that, then you know exactly, you've got all your numbers, and all you do is calculate the length and the width of your shaded rectangle, and that gives you the area under the curve, which is the same as your probability. Now you can also use StatCrunch to solve uniform distribution problems, and we'll be addressing how to use StatCrunch to do that in the next mini lecture. For now, I wanted to show you the old school approach so that you can use it if you want, or if you decide to go the way of StatCrunch, you'll know what the computer software is doing for you in the background when you punch the numbers. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.